This is work that was done largely for John's group, although I think a lot of it is applicable for a lot of other beamlines. And I may be responsible or irresponsible for this, but after my experiences on 11BM, I've been hyping the advantages of using Python as a beamline scripting language. John and I were talking about this, and he had some interest in trying to do more work on 1ID with Python rather than spec. But one of the things that looked like it was going to be an issue was they're already working heavily in spec. They know spec. I wouldn't say they love spec, but they need to. How do we lower the transition barrier, the activation barrier to getting started with beamline scripting in Python? So the goal was to try to write something that would sit on top of what Matt Newville has done, and you heard about 2 days ago with PyEpics, and make it easier for people who know spec and are used to that sort of paradigm to start scripting in Python. So 1ID was at the, when Priya and I were working on this, 1ID was at the top of what we were looking at, although in a couple cases we've added some stuff that they're not interested in. But we want to try to access motors, run scans, scalars, stuff like that in a manner that's similar to spec. We want to reuse spec commands where it makes sense. We're going to use Python syntax. We're not going to use spec syntax. We're going to try to simplify things where we can, so for example, configuration. We want to try to lower the overhead in terms of learning this stuff. I mean, I don't have enough good things to say about PyEpics, but I'm not sure that everybody who wants to run a beamline necessarily wants to go out and learn how to use PyEpics. So I want to make it possible to hide some of that where it makes sense, but by no means prevent people from using PyEpics directly when they need to. Very important from my perspective, you want to be able to simulate stuff. And importantly, and this is something that you can't do right now with spec, is you can't take your laptop home or tell a user to go write a spec script on their laptop and test it unless they have a spec license. They're probably not going to have one. So we want to do something so that you can use this package without having an Epics connection, without having a spec license or something like that.
This is definitely not putting spec into server mode.
We are definitely not. There is no spec here. This is a spec-free presentation. Okay. By the way, I want to say I've nothing against spec, and I think that spec is going to be in the APS for a long time, particularly to run diffractometers. But a lot of what we use spec for is not running diffractometers. So I don't, so in those circumstances, I think it makes sense to at least consider using a full-fledged programming language where you have access to things like MySQL, where you don't have to write a shell around things. Now, Guy will probably argue with some of me on this because he does a lot of this stuff with spec, but it's certainly a more complicated task. Okay. All right. So anyway, you're not going to get away with this without learning Python if you're going to write Python scripts, but we'll see what we can do to make things easier. Okay, so before I go any further, where to find this stuff? These notes will be available, so don't worry about writing all this stuff down, but everything I'm talking about is up on the web. And actually, the documentation is pretty extensive. This is thanks to Pete Jemian, who taught me how to use Sphinx. But let's see if I can get this over here. So this is the actual web page. It's a little bit more usable when you have when you have a higher resolution display. But you can click on all sorts of stuff and get scalar routines will tell you about the scalar routines. you want to find the details of how that works, so on. And let's see, you can even jump from here to the source code and see how it really works, or it was supposed to work. So anyway, let me go back to the talk. Pete, thank you very, very much for the help you gave me with Sphinx. It really made a huge difference. Okay. Likewise, if you want to kill some trees, there's a PDF version that you can print out. Lots of blank pages in it, unfortunately. Okay, so this evolved organically, as they say, and different modules popped up as they started to make sense to add them. And I'll go through them, but the divisions are somewhat arbitrary, but the first one's just called spec, not because it has anything to do with spec, but because it's sort of modeled after things that are in spec. Second one has to do with things that would be in spec macros. Then there's a area detector module, which may or may not make sense for other beamlines, but at 1ID, where they work with a lot of area detectors simultaneously and a number of different ones, this was the approach that made sense. Some routines specifically for working with the GE detector, which has a pretty dumb version of area detector at this stage, so all data ends up in files. And then some stuff that was looking at macros that were used, duplicating spec macros that are in use at 1ID. Okay, so let me go through some of this stuff. First thing you're going to need to do in order to work with this stuff is to configure it. So in order to do that, you're going to need to define where some of the EPICS PVs are. And for work with motors, you define a symbol, whatever you want to call the motor when you're working with it. You give it the IOC name, the EPICS prefix, and optionally, you can give it a string that defines something about the motor. Okay, probably this would have been better if it said, sample position in millimeters or something like that, but I wanted to get it to fit on one line. You can define a pseudo-motor. I'm not sure how much I'm going to talk about that, but a pseudo-motor defined this way can either be a full mapping of n pseudo-motors to n real motors, or it can be an incomplete mapping. So for example, if you have a table and you just want one pseudo-motor, which is the average position, you can do that too. By defining pseudo-motors here rather than defining them directly in EPICS, you have the advantage that if you want to position a couple different pseudo-motors and then launch that, it won't do all of the intermediate moves that would happen if you drive each pseudo-motor at a time. You can also define scalars. That works similarly as you'd expect. And by the way, all these commands will work even if you don't have EPICS, even if you don't have PyEpics. They just will work in simulation mode. What's that? This is a, depends on how you define client and server. All these things. Yeah, so if you are doing this in simulation, it does a little bit of simulation, but it's not actually running any, it's only running a single process. Yes? Right. I intentionally tried to keep away from things like setup files, where you have some a file out there that you would edit to set things up. The way that this is done is that you have the way I would imagine this being used is that you have Python scripts for doing this. So you might have one Python script that defines all the motors in the beamline that would be used by beamline staff, And then you might have another setup script that only defines the motors that you want users to touch. And you can put a clear statement in the beginning of it so that it'll clear out all the other all the old definitions whenever you import the file. So I wanted to keep away from the idea of having a setup file somewhere out in cyberspace. Okay, another kind of setup file that I envisioned was one that would specify what parameters you want to keep track of in the course of an experiment. And you do that by defining logging. You can log all sorts of different things, and I expect this logging list is going to increase as new people come up and say, hey, I want to log this thing. But you certainly will want to log PVs. You may want to directly access scalar channels without having to specify the scalar PV, motor positions, variables in your script, things like that. So you can specify the things you want logged with a bunch of Python statements. And then those things will automatically get logged when you run ascan or dscan, which we'll come back to. And you could also stick into your script the command write logging header, which will cause it to list what the things that it's logging are. And then write logging parameters will have it specify, kick out the things that you've wanted to log in some sort of column format. Absolutely different from the Python logging module. Although it shares perhaps some ideas, but it's definitely not Python logging. I looked at that, but it looked too complicated for what we wanted to do. Why don't you just log everything? I chose. I do that actually, and if you, well, you could do that. I don't log all scalars. You can just tell it what scalars you want to log. It does actually. The ascan actually does log all defined motors before it begins an ascan. But that's different because it doesn't do it at every step. The things that you log are going to be recorded at every step. And because this handle, yes. At this point, you don't have the ability. That could be added, but at this point, it only does. I mean, there's only one type of logging, and that's the things that get done at every point. But in addition, as I mentioned, the motors positions of every defined motor gets stuck in the header. I've never tried to read the output from the ascan here with anything that is that reads spec files. But I tried to follow it closely so that, with luck, things that read spec files will be able to read the output from the ascan here. But I'll be honest, I'm not sure that if I were going to write a data collection program myself, I'm going to use ascan for that. I'm going to probably write my own data collection program, and I may come back to why I would do that. So anyway, here's an example of some code just to give you an idea, where I have in the top box a list of commands that are going to define logging parameters, and then at the bottom a scan that's actually using logging. And so here I write out the header, then I move a motor, I do a loop where I keep moving the motor on a relative basis, launch a scalar, launch a detector, wait for the scalar to finish, read the scalar, and write out all the information that I've asked it to log. And then when I'm done, this is a one ID. Actually, that should say macros, and it's not in macros anymore. That's in 1ID. This is the 1ID stuff. But then tell it to to make a beep to say that it's done. Okay. In terms of the spec-like commands, there are a whole list of things here that work pretty much, well, modeled after what's in spec. But things do use the Python syntax. In spec, you would say MV followed by a motor symbol followed by this position. For this, you would say MV parenthesis, motor symbol, comma, position, close parenthesis. So you're using Python syntax. Around the motor. Actually, generally, no. When when you, let's see, I'm going the wrong way here. Okay. When you define a motor, for example, like I've done here, with define motor 1, like that, you can then say, just simply move motor 1 in the position. You don't, what it's done is it's defined a variable for you. Now, you have to be a little bit careful. What I've done here is this is being done in the spec namespace. Okay, so it's created spec.motor1. And then I have to do another from spec import star so that this is defined as in my local namespace. It's a bit of a kludge, but it works. And if you put this into your you could do that, and I can talk to you later about why I didn't do that. Well, I did it. I think actually, to be honest, what I encourage people to do is if they're going to use this sitting at the console and they're going to type in commands, remove all the flatten all the namespaces, as I've done here. But when you write scripts, keep the namespaces and type that into your names because you'll avoid naming collisions. It's stronger code. It's cleaner code. You will understand better when you come back to it after a year what you're actually doing. Okay. All right. So other things. So moving on to the second module, and module macros. What kinds of things are there? Well, we've talked a little bit about logging. We'll talk about scans, plotting, monitoring, getting user input, and sending an email are all things that are there. A scan is defined to look something like spec. It is relatively straightforward. It will use Matplotlib automatically to show you what you've scanned. It automatically fits to a Gaussian. You use set detector to tell it what detector is being plotted when you run this. You tell it what the scan file is ahead of time, and so on. Here's an example with all the punctuation. So I'm calling a scan here down at the bottom. Let's see, get my mouse back. There I go. Where I have specified it's in macros. The motor that I'm scanning is defined in spec, and I'm telling it what to plot, what the range I'm doing, and I'm giving it a settling time and so on. Okay. You're not stuck with Gaussian fitting. You can define any function you want to. It's perhaps slightly arcane coding to people who haven't done too much work with Python classes, but you define a class which specifies a minimum of two things, how to take the XY data and come up with some starting values, and that's done here. And whatever those starting values are, that determines the number of parameters in your fitting equation. And then you have another function which evaluates the difference between the fitting function and the actual data. And if you define these two things, then you can use refit last scan, pass it the name of this class you've defined, and it will fit it. So here I've taken the previous scan and I've refit it with a sawtooth. And if you look at the code, you'll find the full example code for defining the sawtooth. If you want to plot in scripts, you want to do things a little bit differently. So you do that really in two steps. First step is you define what it is you want to plot. So I want to make a plot of I versus time, and you can't quite read it, but that's what shows up right there as a tab. I tell it what I want to plot, and I want to plot something labeled time, which corresponds to this spec variable. I want to also plot that against two scalars. And then if I run a loop, every time I call update logging plots, it sticks the values into the plot. So that's a simple way to embed plotting into your script. And you can do that for more than one plot. They will just show up as different tabs, like over here. Okay. Something else that came up, which from one idea was, it was clear that there was a need to keep track of PVs, and not necessarily even just when they were running these scripts, but also potentially if they're running a spec script or working even from MEDM. They want to make recordings of what's going on the system when certain PVs changed. So there's a nice feature in PyEpics called monitoring. It's a little bit Python-esque to understand how to set it up. So this is a more friendly interface wrapped around that. But you define something that you want to monitor by specifying where you want the information to go, what PV should change in order to trigger a monitor. So I had envisioned hooking that PV up, for example, to a detector ready signal or state signal, for example. What things you want to monitor when that changes, what PVs do you want to monitor when you change that, and maybe a specific value. Maybe you only want to record this when the when the detector says ready, or when it only when it says counting or something like that. And if you're recording something that changes a lot, you may say, well, I only want to record this at most once every second or once every 10 minutes or something like that. I don't care if the value changes, as long as I've got a snapshot once every, when it changed, you can ignore the next period, changes over the next period of time. So you define all the things you want to monitor with a series of the defined monitor calls, and then you use start all monitors, and the monitoring actually starts. I had envisioned that this would show up in a separate process than the one that might be scripting, running the if you were running a data collection script and you wanted to do monitoring, while I think these things could live in the same thread space, I think it would be safer to start a separate process to do the monitoring. Likewise, you can use that same monitoring approach to do plotting. So you can initiate a plot every time a PV changes. In this case, you do setup monitor plot, and you have a bit more complexity here because you are actually monitoring two PVs, one that says clear the plot if you want to choose to use that, and another one which says plot a new point. The reason that that was set up this way was it could be used as a monitor that would be hooked up to a PyEpics scan record, or an scan record, and that way every time the scan is started, you would clear the plot. Okay. Still uses the same start all monitors as used for monitor logging as well. Okay. Something that one might want to do is get an email message when you have a failure in one of your scripts. Is this something that you appreciate, Matt? Maybe not. Sometimes. What's that? I don't think you get 1,000, but all right. But there is a trick here that helps that I've outlined here. When you set up a script, you get all the input and get all the stuff going that you're going to want to do. You only put your once the measurement, the code that happens once the measurement starts, into a try block, because 99 times out of 100, when you generate that unwanted email, yeah, I knew this crashed because I was sitting there. It's happened while you're in this get input stage. It's only when it goes from the get input stage to the do measurement stage, that's when you're going to walk away. And if it fails while you're in that part of the code, then you'll use the send email message to send emails, or you can also, for whatever brand of cell phone you have, you can find out the email address that corresponds to generating texts. So you have to, well, you know, yeah, you set up your scripting code in such a way so that if you anticipate a particular type of error, you can have a nested try, so that and there's lots of those. Well, if the beamline user isn't going to set up code that's self-recovering, then they'd rather know that the instrument. No, you don't. No, you don't. You don't. Well, there are plenty of cases where John can tell you about where they've collected useless data because an area detector failed to trigger, and at that point, they would much rather know that things failed when it failed. That's your choice. You can certainly do that. In that example, no, but you can do that if you want to. Again, yeah. Yes.
There's some details about sending out email.
Mm-hmm.
The send email. How much configuration is necessary on that? Because sending email from various systems on various schemes.
Well, this is set up. This is set up assuming that you're working on a IT-supported beamline computer, which has access to the APS mail server.
There's one more step. Is it on a Linux computer? Does it shell to the command?
No, it does not. It does no, no.
Python.
It uses a Python library. This uses a Python library with an it uses the SMTP.
They actually run the software on some other machine, but they would need to do the configuration.
Correct. Correct. Yeah. This is written with the APS in mind, or maybe XSD in mind. Let's see. Okay. Well, okay. Well, I know that you can rewrite this very quickly to have sector 15 send mail. Yep. 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 Okay. One thing that became fairly clear that we needed the ability to do was to get input from users. I've spelled out sort of a protocol here of if you follow these steps, things will work. You don't necessarily need to do all this, but if you follow this protocol in your script to get input, then, well, here's a script that does that, and you run this, up at the top you'll see in yellow what actually gets printed out to the user. And they get a prompt with a default value, and if they just hit return, it uses the default value. In the case of the DX, which is the second input thing, you'll notice that it says none as the default, and you can't progress beyond that until you actually type something in. And then at the end, it puts all the numbers you've asked for into this list result down here, and you can get them out, or you could print them out, and so on. So that works that way. The nice thing about this is that I realized fairly quickly afterwards, I could wrap this in a GUI as well. So by just simply changing this variable here, before useGUI was false, to useGUI is true, it pops up a GUI where you can get input values. And that's all you can do from this GUI here, but it allows you to write somewhat more user-friendly scripts where people who were, let's say, more used to modern computers get Windows as opposed to having to, oh my God, you mean I have to type at the command line? So that was relatively easy to put forward. Okay, so that's it for the what's in the macros module. The area detector module, again, starts with having to do definitions. You define area detectors the same way, more or less, that you do for every other kind of thing that we've talked about so far, by defining a symbol. In this case, we have a class of area detectors, and then finally a PV. You may have more than one PV class. You have one to talk to the detector, and then one to get for accessing data, because it allows you different formats. Once you've done that, for every detector type, you can define a series of commands that will access the detector. So for the syntax detector, you define the trigger mode by talking to, and here I use John's notation, the %sign corresponds to the first PV, and if you have a double %sign, which I don't have in the examples, it would talk to the second PV if it's defined. So by doing that, you define a series of commands that each area detector is going to be able to work with. If you don't define a command for an area detector and you try to use it, it will be ignored, and you'll see why that's useful. Okay, so we have a bunch of things that will access area detectors. So if you want to read a parameter, for example, if you want to read the frames parameter for a particular detector, we've defined it here. We can set it with this, and we can read it back with this. So AD_get would be able to read back the parameter from the area detector. AD_set would change it. Done is going to test if things are if the commands have been done. Show sticks together what has been defined. Acquire sticks together a couple commands together. At this point, I think we've identified what sector 1 needs, whether other things are needed to do this at other sectors. I'm not sure, but it's pretty versatile. But it's still in the process of being tested. Okay, to give you an idea of stuff that OneID specifically is interested in, module GE will read image files from the GE and generate ROI values, for example, from them. And it will do plotting and things like that. So to make it easier to work with the GE files, since the area detector itself doesn't pass back the data as at this point.